Okay, for question 3, this was associated with chapter 4, the most recent stuff, so looking at Fourier series. And it says a packaging machine in a factory involves a process where a periodic force is applied to a mass spring system. So there's no damping in this question, it's just a mass spring system. It says the periodic force is a triangular wave as shown in the figure. And notice what I've given you here is I've given you the Fourier series solution to it. So you don't need to go through the maths involved in Fourier series to work out what the solution is, okay? Remember that in the exam, I'm not testing your ability to do maths, I'm testing your ability to understand and deal with vibrations. And so that's why I've given you the answer to that Fourier series. You're probably thinking, great, but what you need to do is you need to go through and you need to find the solution x of t, knowing that that triangle wave has the Fourier series. And so I've given you f of t. And f of t is the sum from n equals 1 to infinity, and n is odd, of bn sine omega nt, where b of n, or bn, equals 8a divided by pi squared n squared minus 1 n minus 1 over 2. So that's the solution for f of t. Okay? Let's zoom out just a touch. Now what's happening in this equation, obviously 8a over pi squared is a constant, then we have n squared on the bottom. This bit here is quite interesting because what this does, it basically flips the sign for every term, okay, so every other term in fact. And so if n is 1, okay, because obviously here n is odd, so we start at 1, next value is 3. If n is 1, then we have minus 1 to the power of 1 minus 1 over 2, so the power of 0, anything to the power of 0 is 1. So we know the first term is positive. When n is 3, which is the second value that we have minus 1, 3 minus 1 over 2, okay? Well, that's going to be minus 1 to the power of 1 half, okay? The square root of minus 1 is that right? Is that n minus 1 over 2? Yeah, this is correct. When n is 3, we have 3 minus 1 over 2, okay? So 3 minus 1 is 2, divided by 2 gives you a value of 1, so minus 1 to the power of 1 is obviously minus 1. So you can see the second term is going to be minus. You then have n is 5, which is the next term, 5 minus 1 is 4, divided by 2 gives you 2, minus 1 squared, positive 1. So it gives you this flipping term. It's the same thing could be calculated using that cosine of n pi, or n minus 1 pi, where basically you get either a value of 1 or minus 1 every other term. Okay, so that's what's going on here. So that's what's given in the question. We now need to find out the solution x of t. Okay, so what we have, basically I'm asking for not the complete solution here, I'm just asking for the sort of the particular integral part of this solution. And obviously it's a mass spring system, so we have xn plus kxn equals our forcing function, bn sine omega n t. Okay, and this is for every n term, so when n equals 1, 3, 5, and so on. Okay, so for when n equals 1, this equation applies. When n equals 3, this equation applies, and so on. And so what we need to do is we need to find a value for x of n, and then obviously sum them together to get the complete solution. And so that's what we're going to do. Yeah, it asks for the steady state solution. Okay, so that's the key that gives you the indication that all we need to find is xpi. We don't need to worry about that complementary function section. And so that's what we're going to do. It's a sinusoid, so we apply the trial function. X of n is alpha cosine omega n t plus beta sine omega nt. That's the trial function. And so x double dot n comes out to be minus omega n squared alpha cosine omega nt plus beta sine omega nt. And so we take those things and we plug them into the equation. So we have minus m omega n squared alpha cosine omega nt plus beta sine omega nt plus k alpha cosine omega nt plus beta sine omega nt equals bn sine omega nt. So we now need to solve this solution to find values for alpha and beta. So what we're going to do is we're going to separate this equation out into two equations, one involving cosines and one involving sines. Since there's no cosine here, all the terms involving cosine must equal 0, and all the coefficients for the sines must equal b of n. So there's our two equations to solve for the two unknowns. And so we can say that cosine omega nt equal times by alpha k minus m omega n squared. Okay. So this is just rearranging this equation. Sine of omega nt, we have beta times by k minus omega n squared, k minus m omega n squared equals b of n sine omega n t. So that's just this equation rearranged, grouping the terms that have cosine omega nt, which is that lot, and then the sine omega nt, and that lot. And because there's no cosine on this side of the equation, okay, therefore this coefficient here must equal 0. And this coefficient here must equal b of n. And so what we can do is we can set those equations up. Alpha k minus m omega n squared equals 0. Therefore, the only way this equation is true is if alpha equals 0. And beta, k minus m omega n squared, must equal b of n. So therefore beta must be b of n divided by k minus m omega n squared. And so we stick this back into our trial solution. We have x of n equals beta sine omega nt. So we have b of n divided by k minus m omega n squared sine omega n t. So there's our solution for x of n. But we're asked to find the complete steady state solution. Well, the next step is we know that x of t is basically the sum from n equals 1 to infinity when n is odd of x of n. And so the next step is obviously to stick in what b of n is. Okay, so there's a sum, n equals 1, n is odd, from 1 to infinity. We have 8a over pi squared n squared minus 1 to the power of n minus 1 over 2 sine of omega nt divided by k minus m omega n squared. And we can simplify this further. We know that 8a over pi squared is a constant, so we can take that outside of the sum. Minus 1, n minus 1 over 2, times by sine, omega nt, divided by n squared, k minus m omega n squared. So there's the solution.